Hello everybody and welcome to this GCSE Chemistry video about equilibria. And in this video we will explore the concept of a dynamic equilibrium. We will then move on to look at Le Chatelier's principle and how we can apply that to various situations. And then we will finish by looking at a couple of industrial examples of Le Chatelier, particularly focusing on the Haber process and graphs. In chemistry, we would typically think of a reaction as one where you start with the reactants and the reaction proceeds and we make the products. However, in reality, many reactions are actually reversible, and that means that they go both ways. They go forwards and they go backwards. And to symbolise that, we don't have the forwards facing arrow, we would have a reversible reactions arrow like this. One of the reversible reactions that you're likely to be most familiar with is when hydrated copper sulfate is heated and is converted into anhydrous copper sulfate and water. You will probably have seen this reaction in the energetics topic, where you were measuring enthalpy changes that can't be measured very easily directly by doing other chemical reactions such as dissolving. Now, in that reaction, the forward reaction is endothermic, meaning the temperature drops, and in this case it requires being heated to make it work. And the reverse reaction, the backwards reaction, is exothermic, meaning that when you add water to the anhydrous copper sulfate, the temperature is going to go up. And that is a characteristic of any reversible reaction. One of the directions will be exothermic and the other will be endothermic by the exact same amount. It's just one of them the energy will go up, one of them the energy will go down. It doesn't have to be backwards is one and forwards is the other. It can totally vary. Now, equilibrium can only be reached in what is known as a closed system. And if you remember from the energetics video, we discussed that that is where energy can be exchanged between the chemicals and the surroundings, but matter cannot. And that could be something as simple as just having a lid on a beaker, so no gases can go in or out. Reversible reactions are usually referred to as existing in a state of dynamic equilibrium. And in fact, that could be a 2-mark question where you're asked to define what a dynamic equilibrium is. And so there's obviously 2 parts to the answer. And so the first part is that the forward and the backward reactions are both occurring at the same rate. And that's the origin of the dynamic part of the definition, that the forwards reaction is happening and the backwards reaction is happening. Now, the equilibrium part is really sort of like a 2-fold part to it. The fact that it's at the same rate, that's one aspect of the word equilibrium. And then the other aspect of the word equilibrium is that the concentrations of all the reactants and products is constant. And so you might not have the same amount of both, but the amounts that you have of reactants and products is unchanged. Now, the best way of visualizing this is actually to look at a graph. If we look at a typical graph of a one-direction reaction where reactants turn into products only, over time, the concentration of reactants will obviously decrease as the reaction goes on. It decreases really quickly at first, then begins to slow down, and then it stops when one of the reactants, or both of the reactants, or all of the reactants have been used up. However, in a reversible reaction, that is different. If we look at the concentration of the reactants, that follows the same sort of path of decrease, but over time it decreases more slowly until the point where it levels out. And it doesn't level out at 0. Who knows exactly where it levels out, but it's definitely not 0. There is definitely some reactants left over. If we were to map the concentration of products in the same sort of way, then obviously at the beginning of the reaction we have 0 concentration of products. Quite quickly we make some products, and then the rate of making of products decreases because the amount of reactant that we've got left over has decreased. So the rate of the forward reaction is going to slow down. So we're going to make less product. And then after a time, the concentration of products will level out and not change anymore. And that coincides with the same place where the reactants doesn't change anymore. And this is the point that equilibrium has been reached. Now, to repeat, it's a dynamic equilibrium because the forwards and the backwards reactions are both happening, but the concentrations of the reactants and products, they have no overall change because the product is being made at the same rate that the reactant is being used. And because the reaction is reversible, that product is being used up at the same rate that it is made as well, and reactants are forming again. So overall, the reactants and products, whilst they're both being made and used, there is no overall change. Now, the position of the equilibrium is very rarely 50-50. There's no easy way of looking at an equation and working out what the position of equilibrium is. You can actually only tell whether there are more products than reactants by doing an experiment to find out how much of one of the reactants or products you've actually got. More on that later. Now, a really good analogy for a reversible reaction in dynamic equilibrium is an escalator. Now, escalators, the moving stairs that you don't have to walk whilst they are taking you in one direction, they will move and you will move with them. And so this is moving downwards. Now, obviously, you shouldn't, probably for health and safety reasons, but probably everybody does. You can go against the escalator. So you can go upwards on a downwards escalator. And if you run fast enough, you will get to the top. And even though the escalator was trying to take you downwards, the upwards won because the upwards was at a faster rate. However, you will, if you're clever, be able to match your upwards walking to the downwards movement of the escalator. And here you have reached equilibrium. You've reached balance because your position, up or down, won't be changing. You will be effectively still whilst also moving, and that's why it's called a dynamic equilibrium, because you are moving, your legs, your muscles are working, and the escalator is working, so the upwards and the downwards are both happening, but your height is not changing because you have reached equilibrium. And you could do that at the bottom where we've got here, so 3 steps up, or you could do this 3 steps down. You could do this in any position, up or down on the escalator. Equilibrium, that position of not actually moving your overall height, your height not changing, that is applicable at any of these steps along the escalator. Just like a dynamic equilibrium might be 90% product and 10% reactant, or any other combination. So that's a really good analogy. You can reach equilibrium whilst walking up a down escalator. I just mentioned that the position of equilibrium could be 40-60, could be any proportions at all. And so I wanted to begin this section by looking at what it is that affects that proportion. And so the position of equilibrium, and that means the proportions or the ratios of reactant to product, is at the point where the chemicals are most stable. And the fact that they're the most stable at this point means that they have the lowest energy. And at that equilibrium, there will be a certain set of conditions, and these conditions will be to do with an optimum temperature, pressure, and any other factors that might happen to be affecting the chemical reaction. Those conditions are such that they are in the most stable temperature, for instance, as well. And so Le Chatelier's principle states that if a reaction at equilibrium is subjected to a change in concentration, pressure, or temperature, the position of the equilibrium will move to counteract the change, which is really fancy sounding, but he was a professional scientist and he wanted to sound clever. However, we can reduce that definition down to something that's more usable, which is that equilibria shift to oppose change. And those few words are really powerful, particularly for your understanding of Le Chatelier's principle. And even in exam situations, it can help your approach to any number of types of question about equilibria. And we should be absolutely clear here. The reason that the equilibrium is shifting to oppose the change is not through any conscious thought. The equilibrium is not something that we can personify. It is doing it to maintain stability. So if we impose a change upon it, that makes it less stable than before, and the equilibrium shifts spontaneously to become as stable as possible. So Le Chatelier tells us that anything that we do to an equilibrium will be opposed by the equilibrium itself shifting. And so what that means is if we increase the temperature, equilibrium will shift in the direction that lowers the temperature, and that is the endothermic reaction. If we decrease the temperature, equilibrium will shift to oppose that, to raise the temperature up again, and that will be the exothermic reaction. From the point of view of pressure, if we decrease the pressure, equilibrium will shift to raise the pressure back up again. And the higher pressure is the side of the reaction that has got the greatest number of molecules of gas. And if we raise the pressure, equilibrium will shift to lower the pressure back down again. And that will mean that the reaction will shift in the direction where there are fewer molecules of gas. And finally, if we increase the concentration of a particular chemical in the equilibrium will shift in the other direction to decrease the concentration of that reactant or product. And it follows that the exact same thing is true if you were to decrease the concentration of a particular chemical. The equilibrium would shift to increase its concentration to make more of it, and that means it would shift to the side that has got that particular chemical, thereby making more of it to restore that most stable of conditions, which is what all of these shifts are to do. Now is probably a good time to point out that the square brackets around a particular formula, such as square brackets around X, means concentration of chemical X, and that is just a shorthand notation for that, which definitely makes things a bit faster and is totally fine to do in an exam situation. Now, I haven't mentioned catalysts until this point, and the reason that catalysts are less significant is that they have no effect on the position of equilibrium. The reason that this is true is obvious if you consider a reaction profile. So if we have a look at an exothermic reaction profile in the forwards direction, you can see why this reaction maybe is reversible, because the energy barrier, the activation energy in both directions, is not particularly big, which is what allows both the forwards and the backwards reactions to happen. However, what catalysts do is they lower the activation energy, and if you consider the reaction profile, the activation energy gets decreased by the same amount for both the forwards and the backwards reaction, because the hill just kind of gets lower, so to speak. And so the forwards reaction and the backwards reaction will be sped up by equal amounts, and so all that would happen is equilibrium would be reached faster. Let's take a look at a couple of examples of equilibria and how they would be affected by the changes that we've outlined here. So in the first example, we've got oxygen and sulfur dioxide producing sulfur trioxide, and the delta H is minus 200, which we need to take a moment to process as meaning it is exothermic. And that's really important for this first question. If we increase the temperature, equilibrium shifts to decrease the temperature, which is in the endothermic direction, so to the left-hand side here. So equilibrium shifts to the left-hand side. For part B, if we decrease the pressure, equilibrium shifts to increase the pressure, and so it shifts to the side with the greater number of molecules of gas. And there are 3 on the left-hand side and only 2 on the right-hand side. So the side on the left-hand side is the higher pressure side, and so shifting to the left, which is what happens, has the effect of increasing the pressure. And finally, adding a catalyst, well, that's a trick. Adding a catalyst has no effect on the position of equilibrium at all. On to the second example. If we decrease the concentration of hydrogen iodide gas, then the equilibrium will shift to replace it, to make more of that hydrogen iodide gas to try and restore the balance of concentrations to reactants to products. And so that means it will shift to the right-hand side. And then the final example of increasing the pressure. Well, equilibrium shifts, if it can, to decrease the pressure. Now, it can't actually do that here because there are 2 molecules of gas on the left-hand side and 2 molecules of gas on the right-hand side. So the pressure of both sides is equal. And so increasing the pressure, or decreasing it in fact, would have no effect on the position of equilibrium, although, it should be pointed out, it would affect the rate of reaction. We're going to finish this video off by looking at some industrial processes and looking at how we can maximise the yield of a particular target chemical whilst not really putting the rate of reaction under any negative impact. Unfortunately, this isn't always possible, and it's really important that you can appreciate that sometimes we have to have a compromise between the amount of product that we make, which is the yield, remember, and how quickly we get that product, which is the rate of reaction. And something to note from the get-go is 100% yield, if it takes a month, is not as good as a 10% yield if it takes 1 day, because over a 30-day period, in method 1, you get 100% yield, which sounds good. But in method 2, you get a 10% yield every day for 30 days, so that's 300% yield for purposes of comparison. So method 2, even though it sounds less good on paper, it gets us 3 times the amount of product over the same period of time. The first industrial process we're going to look at is the synthesis or production of methanol from hydrogen gas and carbon monoxide. And so this reaction, as you can see from the equation here, involves 3 molecules of gas turning into 1 molecule of gas, and the forward reaction is exothermic. And so we can use our knowledge of Le Chatelier to work out what the optimum conditions would be to maximise the yield of methanol. So we need to think, first of all, about what we want the equilibrium to do. Whatever we do to the chemicals, however we manipulate the conditions, we want to make the equilibrium shift to the right-hand side. So the equilibrium needs to be shifting in the forwards direction. Now, the forwards direction involves an increase in temperature because it's exothermic when we look at that delta H value. And so it would follow that if we want the equilibrium to increase the temperature, before it does it, we need to first lower the temperature and have a low temperature reaction, and that would favour the equilibrium shifting to the right. Also, the forward reaction involves a decrease in pressure because the right-hand side is lower pressure than the left-hand side. And so to make the equilibrium shift forwards to decrease the pressure, we first need to have a higher pressure to maximise the yield of methanol. Now, in practice, we use a high pressure, about 50 to 100 atmospheres, so that means about 50 to 100 times higher pressure than atmospheric pressure, and that gives us both a good yield and a fast rate of reaction. We use a temperature of 250 degrees C, which is not low, but from an industrial point of view, it's not a high temperature. And that's because we want to try and maximise yield. Remember, we'd ideally want a very low temperature, but we don't want to compromise on rate of reaction, because remember, a higher temperature is a faster rate of reaction. And so to make up for the fact that we are compromising on the rate of reaction, we include a catalyst, which is a mixture of copper, zinc oxide and aluminium. And that helps us to get over our compromise that we're having to do. So we're trying to keep the temperature as low as possible without reducing the rate of reaction too much. One final process that we're going to look at is the manufacture of ammonia. Now, I wouldn't normally ever give an A-level student word equations, but the reason I'm doing that is because I want us to discover some things about the synthesis of ammonia from a graph. And so in exams, they often give you graphs for you to either interpret in a short-term sense or give detailed analysis. So let's look first of all at general patterns on here. So we've got on the graph, as we increase the pressure going from left to right, the percentage yield of ammonia increases. So as we increase the pressure, the percentage yield goes up. All of these are different forms of sort of positive correlations. So because yield increases when pressure increases, we know that the forward reaction involves a decrease in the number of molecules of gas, because that is the only explanation for a higher pressure making the equilibrium shift to the right-hand side, because the forward reaction must lead to a lower pressure. The other clue that we've got is we've got 4 separate lines on our graph at different temperatures, and we can see that the highest temperature gives us the lowest yield at the same pressure. So if we consider one particular pressure, let's say this pressure here, the yield for 500 degrees C is significantly less than the yield that you would get for any of the other lower temperatures for the same pressure. And so, because the greatest yield is found for the lowest temperature, that must mean that the forward reaction is exothermic, because a high yield is favoured by a lower temperature. So the lower the temperature, the more the equilibrium is able to shift to the right-hand side to maximise that yield. So we can look at this graph to deduce that the forward reaction involves a decrease in moles and involves an exothermic process. We can also use this graph in a bit greater depth to make some suggestions about the temperature and the pressure that we should use, or to justify the pressure. So for instance, if we look at the top line, after maybe this pressure here, there is no point increasing the pressure any further because that will be really expensive, and there's very little difference in rate of reaction in this entire tracking on here. It's not quite flat, but it almost is. You get the greater difference in yield at the higher temperatures. And so, in reality, the temperature that we use for the Haber process, where we make ammonia, is actually between 400 and 500. We usually use around about 450 degrees Celsius, which would have a similar line like so. And we use this temperature for 2 reasons. First of all, it is not really high. Certainly as we go higher, 600, 700, etc., the yield will get much lower. So it gives us a decent yield of ammonia. But what it doesn't do is give us a slow rate of reaction. If we went right up to the top at 200 degrees C, we would get a very good yield, no question about that, but we would get a slow rate of reaction. So 450 degrees Celsius gives us a balance or a compromise between a good yield and a good rate of reaction. And the pressure that we use is around 200 atmospheres of pressure, written as ATM. Now obviously there's no numbers on my x-axis, but 200 atmospheres isn't very high, but the reason that we do that is it gives us a good rate of reaction and a good yield without being dangerous and expensive, particularly the expense of the equipment needed to reach a higher pressure is quite significant. And so overall we've got our compromise between yield and rate of reaction as well as cost. Okay, that's all for this video. See you again soon. Bye bye.